Welcome back to the class on electrical mechanics. In this lecture, we are going to discuss about the numerical part 4. A three-phase, four-pole, four-party RPM 50 Hz induction motor has torque on a rotor winding of having a resistance of 0.2 ohms per phase and standstill reactance of 1 ohm per phase. When starter is energized at a rated voltage and frequency, rotor induced EMF at a standstill condition is 120 volts per phase. Calculate the rotor current, rotor power factor, or both at a starting and running. The per phase rotor current at a standstill condition I2 equal to E2 by square root of R2 square plus X2 square. All these values are given in the numerical, that is Et equal 120 volts, square root of 0.2 square plus 1 square. To simplify this one, we are getting a 117.67 ampere. The rotor power factor is standstill condition cos theta 2 equal to R2 by square root of R2 square plus X2 square. Substitute all the values, we are getting the 0.19. So whenever we want to find out the rotor current in a running condition, then you have to find out the speed. The synchronous speed ns equal to 11 ds per p. Substitute all the values, you're getting the 1500 rpm. The slip of the induction motor SFL equal to ns minus n by ns. Substitute all the values, you're getting the 0.04. Now the per phase rotor current in a running condition, IR equal to SE2 by square root of R2 square plus SX2 whole square. Substitute all the values. Here we already calculated slip of the induction motor, that is 0.04. We're getting a 23.53 ampere. The rotor power factor at a full load cos theta t equal to R2 by square root of R2 square plus SX2 whole square. Substitute all the values, we are getting a 0.98. Now you have to calculate the torque output induction motor at the time of starting as well as the full load. Synchronous speed in radians per second equal to 2 pi ns by 60. Ns is 1500 rpm. If you substitute that value and simplify, you are getting the 55. The torque output induction motor at the time of starting equal to 3 by omega s. I2 square R2 by 1. I2 is nothing but a rotor current at the time of starting. Substitute all the values, you are getting the 52.9 Newton meter. Same formula you can use to find out the torque output induction motor at a full load also. T full load equal to 3 by omega s IR square R2 by s, where IR is nothing but a rotor current in a running condition. Suppose induction motor is nothing but 0.04. Substitute all the values, you will get in 52.87 Newton. The ratio of starting to the full load current I2 by IR, already we calculated the two values, substitute all the values, you will get in 5. Ratio of starting to the full load torque TST by T full load, that is equal to 52.9 by 52.87. We are getting the 1. If external resistance of 1 ohm is per phase is inserted in the rotor circuit, calculate the rotor current and rotor power factor torque at the time of starting. Suppose if we add the 1 ohm of external resistance into the rotor circuit, what is the value of rotor current and the rotor power factor and torque at the time of starting? The per phase rotor current at the time of starting equal to E2 by square root of R2 plus small r whole square plus X2 square, where smaller is nothing but a per phase external resistance added into the rotor circuit. Substitute all the values, we get 76.82. Rotor power factor at the time of starting, that is equal to R2 plus RR divided by square root of R2 plus smaller whole square plus X2 square. We're getting the 0.768. Starting torque, when you add the external resistance into the rotor circuit, T starting equal to 3 by omega s into I2 square into R2 plus smaller by 1. Here I2 is nothing but this current 76.82. Now substitute all the values here, you're getting the 135.35 Newton. Now if we come to the second numerical, a 3-phase 6-pole 50 Hz induction motor has a full load speed of 960 rpm. If the springs are short circuited, motor drives at a constant torque load. The speed is reduced to 800 rpm and 400 rpm by inserting external resistance into the rotor circuit. Compare the rotor copper loss at this value of speed and compare to the full loss. So whenever you are saying the constant load torque, air gap power is constant because the synchronous speed is constant, not the power. Synchronous speed is constant. For constant air gap power, so the rotor copper loss is proportional to the slip of the induction motor. So slip at a full load equal to ns minus n by ns. So whenever you are saying the frequency is 50 Hz 6-pole means the synchronous speed becomes 1000 rpm. You take that value. And the full load speed is nothing but 960 rpm. Substitute that value, you are getting 0.04. Slip at 800 rpm, that is equal to 1000 minus 800 by 1000, you are getting 0.2. Again, the slip at 400 RPM, you're getting the 1000 minus 400 by 1000, you're getting 0.6. Rotor copper loss at 800 RPM by rotor copper loss at 1000 RPM, that is equal to slip at 800 by slip at 1000 RPM. So you're getting the 5. The same manner, if you find the rotor copper loss at 400 RPM by rotor copper loss at 1000 RPM, that is directly proportional to the induction motor. So 0.6 by 0.04, you are getting the 15. A 10 kilowatt 400 volt 3-phase 4-pole 50 Hz delta connected induction motor is running at no load with a line current of 8 amperes. The input power of 660 watt. At a full load, the line current is 18 amperes. The input power is 11.20 kilowatt. Stator effective resistance per phase is 1.2 ohm. The fractional windage losses is 420 watt. Neglecting the rotor copper loss at no load, calculate the stator core loss, rotor losses at a full load. Whatever the power is taken by the induction motor at no load, some amount of power is wasting as a stator copper loss, and some amount of power is wasting as a stator core loss, and some amount of power is wasting as a rotor copper loss. We can neglect the core loss, and remaining power is wasted to meet the windage and factor. But in the numerator, it is given that rotor copper loss also we can neglect at no load. So stator core loss equal to no load input power minus no load stator copper loss minus windage and fractional loss. So the stator core loss equal to the input power taken by the induction motor, that is given 660 minus 3 into, because it is a 3-phase induction motor, this current is nothing but a per phase current. At no load, how much current is taken by the induction motor means 8 amperes of current is taken, but the stator winding is connected in delta, so the per phase current becomes 8 by root 3 whole square into stator resistance 1.2. So 3 into 8 by root 3 whole square into 1.2 minus windage and fractional loss also given 420. So we simplify this expression, finally getting the 163.2 watt. 8 gate power at full load, that is equal to stator input power minus stator copper loss minus stator core loss. So the stator input power is given 11,200 watt minus, so this quantity is nothing but stator core loss. Now this quantity is representing the stator copper loss. 3 into the full load current is given as a 18 amperes, so per phase current becomes 18 by root 3 whole square into 1.2. So finally, if we simplify this one, you're getting a 10,648 watt. So the total rotor losses equal to rotor input minus shaft power. AJ power is nothing but a rotor input power. 10,648 minus shaft power is given, that is a 10 kilowatt in the numerator it is given. So minus 10,000, it gives the 648. The total rotor losses is 648 watts. The total rotor ohmic losses at full load. Rotor copper loss equal to rotor losses minus windage and fractional loss. So whenever you are saying the rotor losses, it is consisting a rotor copper loss as well as windage and fractional loss. So rotor losses minus windage and fractional loss gives the rotor copper loss, that is equal to 3 into I2F square into R2 equal to 648 minus 420, we are getting the 228 watt. I2F is nothing but a rotor current at a full load. Speed, internal torque, and shaft and efficiency of a induction motor. We want to find out the speed. This is nothing but a rotor copper loss divided by the slip of the induction motor, that is equal to the air gap power. So the slip of the induction motor equal to 3 I2F square R2 by air gap power. We know all the quantities. Substitute in the numerator as well as denominator, we are getting the 0.0212. Once we know the slip of the induction motor, then we can easily find out the speed of a motor. N equal to ns into 1 minus s. Substitute all the values, we are getting the 1468.2 RPM. Internal torque. The internal torque is nothing but a 8 gate power divided by the synchronous speed in a radians per second. Already we calculated the 8 gate power, that is 10,648 divided by 50 pi. If we simplify this one, we are getting 57.79 newton. Shaft power is nothing but how much power is available at the shaft divided by the angular velocity of the shaft in a radians per second. So here the shaft power divided by the omega suffix r, we can write it as omega s into 1 minus s. Again, substitute all the values. Finally, you are getting 65.04 newton. The efficiency of the motor equal to shaft power divided by the input power of induction motor. 10,000 divided by 11,200. We're getting 89.2%. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of the YouTube channel so that I'm always welcome to answer all your questions.